Thank you very much for being here. It's a pleasure. For me, Brain Modes is like this special conference where you can understand what I'm trying to understand in the brain. And so I'll guide you here through this exercise where we're used to look at the brain as a network, but there's some evidence pointing to there may be other phenomena that we are missing out. So this is a bit a provocative title, but I hope I will convince you that there's some sort of wave mechanics going on that we should be considering. So as briefly as an outline for my talk, if this should work. Okay. Yes, it just worked before. Okay. Anyway, well, yeah, okay. So briefly as an outline, I will show you a bit of what we're finding through experimental observation, where we're finding these brain modes and we still don't entirely understand where they come from. So in terms of mechanisms, the mainstream idea is that they emerge from neural network interactions. So we've been doing some models of dynamical interactions in the structural connectome to see how this could explain these patterns. So this mechanism remains valid until refuted, but at the same time, there's an alternative mechanistic explanation that is gaining some momentum, proposing that this is related with some resonant waves in the brain continuum. So there are also some models or analytic predictions for this. So at the same time, this is also remains a valid hypothesis. So we're a bit in between, like what do we choose, right? Are these two ways to look at the same thing? So I did some experiments, particularly with the ultra-fast fMRI imaging. So I will go deeply into that and also show you some results. I'm finding more recent results using biomechanical modeling. So in terms of brain, like what are these brain modes or intrinsic brain modes or resting state networks, intrinsic connectivity networks, functional gradients, there are different names to give to them. They've been reported already for over 20 years. You all have heard probably about the default mode network. When I started, there were entire conferences dedicated to the default mode network. But the thing is that we still don't fully understand where it comes from, right? I like that Marcus Reichel proposed the name the brain's dark energy, in the sense that, yeah, it is some form of energy that is organizing the brain in these patterns. But the truth is that many years have passed and we still lack a complete understanding. So what we know now is that these modes are consistent. We find them consistently across hundreds of studies. I've analyzed over 30 data sets and I always find these modes with different techniques, and they are meaningful, meaning that they appear altered in neurological diseases, psychiatric diseases. They change in different cognitive functions. So it's in this resting state activity, but what do they mean? So they're being used for precision psychiatry, let's say, for diagnosis, have been proposed as biomarkers, but we need a better understanding. So one way to look at this, so there are different ways to obtain them and to capture them, but I wanted to look more deeply and see what we can get from the signals. So we can look at the signals over time, for example, have some snapshots of the activity over time, and we see some recurrent patterns that we just saw this morning, the talk from Shella also showing that when you average, you actually see a pattern that seems to relate with the default mode network. And I developed an algorithm to kind of identify the time points at which this network was active. So in a way, we do a pattern of phase coherence at each time point, and then we cluster these patterns into a finite number of modes, let's say, and then we quantify the probability of each mode in a given scan. Now, the thing with this leading eigenvector dynamics analysis is that the eigenvectors are, in a sense, agnostic to the sign, which means that this and this, it's the same pattern, right? So you can have the mirrored version. So whereas coactivation patterns, they sometimes come in pairs where you have one coactivation pattern that's anti-correlated with another. Here, LIDA puts them together in the same bag, like they are both expressions of the same pattern. And this we can then use measures where we quantify the occupancy of each mode, depending on how many you choose, but in a way you get the probability of occurrence of a given pattern in a certain scan. And this has been giving like nice results. This is an example, for example, of the patterns we obtain. Like if we choose k equal 8, I mean 8 modes, then I'll go how we decide the number of modes. But if we cluster into 8 patterns, the first pattern that the algorithm detects is a global mode where all the signals are aligned in phase. There's no anti-phase relationship. So everything goes together, everything goes down together. Then there is the second mode, more or less, well, the default mode network. These are different slices of the default mode network, but we see clearly this pattern that we know is the default mode, the visual network, the ventral attention. So this overlaps with the 7 resting state networks identified in a certain template. It's the EAO template, but these are how they look using this algorithm. So they are very well defined in space. And then how, for this type of analysis, when we're comparing data sets, so this is from the ABIDE database where we have over 1,000 scans from controls and participants from the autism spectrum. And what we want is to see, is there any of these patterns that maximally differentiates the 2 conditions? Can we associate one of these patterns or more? So what we do, the algorithm, we cluster into 2, into 3, into 4, into 5. And for each clustering solution, we compare the probability of occurrence in controls and in patients, or in condition A and condition B. And then we do a statistical analysis. We use a permutation test, and this threshold here is the Bonferroni corrected test. So it means that these can be considered true positives, the blue ones, like the smallest p-values. This goes down to 10 to minus 7, right? And here I color the bars. So here it's not very clear, but we identify a pattern that across different clustering solutions, the same pattern appears to be significantly reduced in patients with autism spectrum disorder. And how does this pattern look like? Well, it looks like the DMN, right? If we look at the list of brain areas, it's really the left and right posterior cingulate, the left and right angular gyrus, and the left and right frontal medial orbital sulcus. So there's a clear difference. It's statistically significant. So, and this also corroborates previous findings that have associated the default mode network with many neuropsychiatric disorders. But the mechanisms are unclear, and it's crucial to understand, because it's the only way we can then design therapeutic interventions to target these patterns. Also, they are very consistent. I mean, I've analyzed different data, even a data set from China, for example, where we find again the same patterns. Here is if we cluster into 5, and we had 4 different sessions. In each of them, the same 100 participants are scanned. And in the 4 sessions, when we cluster into k equal 5, so this is run independently, we get exactly the same patterns. So they're consistently there. So there's high consistency. And again, I wanted just to call out this attention that there's always this global mode where all signals co-vary in phase, so instance of time where everything goes in phase. And then whenever we see other patterns forming, the signals in some brain areas shift out of phase from the rest of the brain. And so it's a dynamical system, so we decided to apply some methods from dynamical systems theory, like transition probabilities, Markov chain transition graphs. So how this works is, when you're in state 1, what's the probability that in the next time point you're still in state 1? So this is like 77%. So this is the global, let's say, nothing is differentiating and you're here. Then once you with some probability, you can switch to state 2 to the DMN. Once you're there, you can remain there in the next time point, and then you either decay back to state number 1, which always have more probability to decay back to state number 1 than to switch to any of the other states, or you can switch to the other states. But mainly this thing that this state here is more stable and all the others eventually decay there suggests in this strange attractor system that this is a kind of a main attractor, and the others are more like considered ghost attractors. So this is what we came into, it's pseudo attractors in the sense we recurrently visit them, they appear consistently across scans, across subjects, but they're not like stable in the sense that you're stuck in them. But well, this is trying to gain insight. Then we found that, okay, the probability, for example, of being in that global mode pattern is higher in people with good cognitive performance. This was in healthy elders, whereas the occurrence of other patterns increased with people with poor cognitive performance. Again, this same global pattern that was increased in best performers was decreased in people with schizophrenia, the stability of this one, and they had more excursions even during rest to other network states. Another example, for example, in depression, in patients in remission from major depressive disorder, they had significantly higher, in this case, occurrence of a network pattern that was like a default mode, but more diffuse default mode network. So, and that connected with the subcortical areas. So there is something that maybe, indicating that these networks have a function, they are consistent, but we, again, still don't fully understand. So the main mechanistic hypothesis for this functional network, so we know there is a structural network, we are in the era of connectomics, let's say, and so the most obvious solution is to consider that they are related. So we would see like the activation of one pattern would be like a cluster in this structural network or in another, and the correlations come from like co-activations of hemodynamic response functions that would drive the activation of these networks. So how to test these hypotheses? So how is this link between the functional network and the structural network? Well, we can try to look for modularity or for eigenvectors of the structural connectivity matrix, but actually they don't give a perfect fit because, as we heard these days and yesterday, well, the interactions between neuronal populations are nonlinear, so we usually think we need a mathematical model. That's where when I started my PhD, was to develop this type of brain network models informed by tractography. We have the links, we parcellate the brain, and then we know how strongly some areas are coupled together. We can consider also delays, and then we have some sort of nonlinear dynamics at each node, and also we can use different types. I'm here putting a pool of different models that have been used. They all have this coupling term that is scaled by the structural connectivity in the end. And in general, as an overview, because I tried to make like some reviews, of course, each model is slightly different from the other, but the idea is that you have, you are in this critical range between. So you have a model. In this case, it was the Kuramoto model of coupled oscillators that I used during my PhD. I've also used more evolved models. But the idea is that when the coupling strength, this global coupling here, is too weak, sorry, everything is asynchronous, like the nodes are very independent. If it's very strong, everything is synchronized together. But when you have a critical range, sorry, of coupling, you can have like this, what is called metastable cluster synchronization, or different types of sort of formations of stable solutions that are weakly stable. And it's in that critical range that we think the brain is operating. We simulate these dynamics, and then we generate functional connectivity. Sorry, this is okay. So this would be the structural connectivity from a given brain area. This is the experimental functional connectivity, like what these areas are connected. And we see that for some specific seeds, the model performs quite well. Here are two different seeds. Here is also like the structural connectivity here, the experimental functional connectivity, and the model functional connectivity. So there's some degree of correlation. There are some patterns that seem to be very well reproduced. But the truth is that we still, and I know most of the models, we still don't get exactly the default mode network or the dorsal attentional network. They're not really coming out from the models alone, unless we do a lot of weight fitting and optimization of parameters. But just using the raw structural connectome, it's not coming. But still, this low spatial fitting is generally attributed to failures in tractography, especially capturing long-range connections, because these resting state networks are very symmetric, right? We know that, we see that there's a lot of symmetry across the hemispheres, and that's where this is failing. So the thing is, this mechanism becomes valid. The fault for bad fitting may be due to the structural connectivity, but at the same time, and sorry, there is another one. And also these models also manage to model these switching dynamics. They also provide insights of what is going on. So in the sense, the network structure has multiple stable solutions or multiple weakly attractor states, weakly stable states, and the dynamics is constantly switching between these states, either spontaneously due to the natural heterogeneity in the networks, broken symmetry, or if you just add noise and the system has multiple attractors, what is found is that you can switch between a state A to a state B and then return to state A over time. This is like this time versus time functional connectivity dynamics that has been modeled, and you can find different patterns of connectivity. But the thing is that these patterns don't actually match so well the functional connectivity. So that is what the things. There is something that is not very well explained with these models, is why when you get increased correlation of activation in one side, you have a deactivation in other brain areas. Sometimes you have these increased signals and decreased signals like this. And these coactivations and deactivations point to a different phenomena, this wave phenomena, let's say, which means they are proposing desire excitation of eigenmodes of the brain, so intrinsic modes of vibration, let's say. And these are fundamentally distinct scenarios that are under debate in the field. So I wanted here to give a little bit of teaching, let's say. I think this is missing in neuroscience. This is a lot in acoustics, for example, but resonance, like we can call them eigenmodes, resonant modes, harmonic modes, stationary or standing waves, even modes of vibration. This is a universal principle in bounded systems, and it obeys to rules from continuum physics that are not necessarily, you don't need to know the details of the constitutive elements of each part of the system. This is something that emerges at the entire systemic level. So one property that occurs, for example, in modes is that you usually have a global fundamental mode where everything is in phase, and then you have harmonic modes where the system can have like this kind of gradients where it's kind of polarizes in a sense, because you have antipoles, let's say, of the system, but they can be spatially distributed. And this can occur in different forms in nature, in different shapes, in lines, in membranes. These are like room modes. Even when I'm talking to you, there are vibrations of sound. So this expresses in many forms. Every system has its own repertoire of resonant modes or intrinsic modes, and they are defined in space, but they oscillate in time. Keep the key oscillating. I put it in red because it will come back at some point. So the eigenmodes, you can excite them by perturbing them at the eigenfrequency, at their own frequencies. So if you just perturb at that frequency, you should see that mode resonate. Also in music, you can just play with a drum, you just apply a single pulse and you can activate a given mode. But also, if you perturb with noise, with white noise, which contains all frequencies, eventually you'll see the modes resonate, right? You perturb with white noise, and usually you can see peak frequencies that come out from the system, which are the eigenfrequencies. Now, here in the animations, they are in a limit cycle. They're always oscillating. They're not damped, but in nature, usually when things oscillate, they decay over time. They are damped, so it's like this. Also, yeah, as I mentioned before, the harmonics, they kind of create these phase locking patterns that are not necessarily full synchrony. Now, if you have like this stochastic eigenmode excitation, even through noise, for example, in a system, you'll see that whenever an eigenmode excites, it will drive correlations and anti-correlations if you certain voxels, let's say, or pixels on the space. So this idea that brain activity or the signals we capture are associated with eigenmodes is back from the 70s and 80s. So this is just an example. But for EEG and MEG, I found this picture nice, but people have been using simple models of spherical harmonics. Even drops of water can resonate with this type of shapes. And so the idea was to propose that the signals and the wave patterns we see even with EEG and fMRI could be linked with this type of phenomena. And more recently, as we've heard already here as well, and people have proposed that what we're seeing also, these modes from the brain could be in resting state activity with fMRI, these ultra slow modes could be linked also with eigenmode excitation, and for that they use the surface mesh of the brain, so like a survey, and they calculate what would be the modes of vibration of the system using an operator. So the pure Laplacian is through 3D space, but if you just have the surface, you can estimate it using an operator called the Laplace-Beltrami, and it predicts these modes. But things can be more complicated than that. And one thing is that even those modes, although they also have the antiphase and things, they don't show the default mode network clearly or the lateral frontoparietal. So there's still something missing. So both of them are missing. Yeah, in the sense that this excitation of these wave patterns drive long-range correlations. I just wanted to make a point here that in wave physics, nodes are not the same thing as nodes in networks. Nodes are the points of no motion of a standing wave. So you can have fixed boundaries at the boundaries, but then it can also create nodes in the middle that are not there. If you just look at the chord, you cannot find them, but once it vibrates, you can identify. And that's where the sand accumulates in Chladni plates. It's in those nodes, but because the others are moving a lot. So what is moving and oscillating in time are the antinodes. This is what it's called. And also neighboring antinodes go in antiphase, so they can create this type of anti-correlated and correlated patterns. Okay, so we have these two, and then it's like, but what can we get? Like if we look at these signals, like are they activating just as a periodic fluctuations, like activation of the anemodynamic response, or can we really see there that they're like damped oscillatory behavior, right? So if we look at fMRI signals, trying to look at it, it's very noisy. The temporal resolution is too slow, around 1 second. So we can see from time to time patterns like the DMN appearing there, but we don't see, it's hard to say if they oscillate or if they just activate following the typical hemodynamic response function. But actually, there have been insights from rat experiments, as we saw from Shella, and there were things that I was kind of looking obsessively to videos like this one. So there's a consensus now that in rodents, in rats, even sedated, anesthetized animals, you still see these patterns of activity, and they are very qualitatively similar, although spatially not, but to resting state networks. So they've identified this default mode network and other networks in rodents as well. But we see in these videos that there was a positive activation followed by a negative activation. It looked like some sort of periodicity. And even in videos like the one that Shella's, this was another talk from Shella, that I could see here like these waves, you see like it turns red, then it turns blue. But again, the temporal resolution is slow. This was actually a correlation with an LFP. I know it's not exactly the same, but this is to show that I was looking at this, you know, and trying to see if we could get something. And then I thought, no, we need to go faster. We need better temporal resolution. I want to see if these are oscillations. And even if the oscillations are slow, if you sample low, you don't have many time points, and you don't have very good frequency specificity because you can miss the peak of the wave, right? If you have a TR of 1 second. So it's not very well aligned. So we did single slice imaging. So we chose a slice that typically we see very well the default mode network. And like this, we can drastically accelerate the temporal resolution of fMRI, because usually you go like all slices one by one, like tick, 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 and then you start again in each TR, you do like 100 slices, and here's like you fix the slice, there's no more noise inside, it's like, and always in the same slice, and we got like 16,000 frames in 10 minutes scan. And the TR was 38 milliseconds. So just to show you a bit the signals that we see. So we see the same wave patterns that we could see in previous rat experiments. There's something here. Here I'm showing 3 different rats just to in the same condition, just to show that there's something here. It's not just pure noise, and there seems to be some oscillatory phenomena. So the first type of, so we don't know, there's traveling waves, standing waves, there's still the question. So we did power spectrum analysis. So we had 3 different conditions. First, the animals were lightly sedated with something called medetomidine that has actually been reported to increase the amplitude of the fMRI signals and these oscillations. And then we give a bit of isoflurane. They are scanned again twice, and then we increase the isoflurane to 3%. And then 2 of the animals were scanned post-mortem. So here is where we have power. So the animals breathe at 2 hertz, or even in deep anesthesia at higher frequencies than this, near 1 hertz, and the heartbeat is 5 hertz, so it's another range. Here is where do we have power in each of these different frequency bands. So in the postmortem, there's no power, there's a bit of noise here at low frequencies, but we see that in the sedated animals, there's power here in the cortex. So this is the cortex. I will show another image of anatomical image to give you better, but there's clearly like high amplitude oscillations that we can detect in the sedated animals that are slightly damp, like lower in the light anesthesia when we add isoflurane. But then when they are at isoflurane 3%, we completely lose these oscillations, especially here. These are like statisticals. This is the p-value 10 to minus 7, highly survives von Ferroni. So all 12 scans show high power at these frequency bands here. Wait, I have here a thing. For example, here is where we differentiate the best between the conditions. And we see that there's clearly some oscillations that are present when the animals are less anesthetized, and that vanish when they are anesthetized. So if we filter in that frequency range, like at 0.2 to 0.25, and here the mask is only where do we have power at these frequencies, above noise levels. And so we clearly, we are seeing better these waves, right? They corroborate what has been previously finding, but we are reaching better temporal resolution that allows us to then do different types of analysis, especially in the frequency domain. Here, just also a note that, yeah, this is the rat cortex here. So this is almost like one convolution here in our human cortex, but the material is similar, right? So it's the same thing, just the scale is very different. So we decomposed into modes with, this is just principal components are the eigenmodes of covariance. And so what we did was we did the same, the eigenmodes of covariance from the post-mortem animals, and we get the largest eigenvalue on that, you know, like and that's our threshold. So these are the 10 modes that survive that have an eigenvalue higher than the eigenvalue in the post-mortem scans. And so these eigenvectors, we can project them in the slice, in the voxel space, okay? And they switch, we can get their temporal signature by projecting, again, these vectors into the signal. Again, we get a temporal signature. It's like the weight over time of each of these patterns. And what we find is that it is switching between positive and negative values with sustained periodicity. Some with much more. Here we see very clearly, well, I will now show another figure where we should see this better. But just to see that we see in the signal some oscillations, and when we decompose into modes, we can find these oscillations even more purely. For example, here, I'm putting here, so we have the spatial, so these are the eigenvectors, then the temporal signal, this is when we project the eigenvectors into the time series, and then we can do the power spectrum of this time series. In red is the time series of projecting this into the post-mortem scan, so just to show that this is really alive. Now, if I multiply this pattern by its temporal signature, right, we clearly see this oscillation in time. So it's not a property of principal components that the coefficients oscillate in time with sustained periodicity. There are other interesting things, like we can have other modes that don't necessarily resonate or oscillate in the cortex within cortical boundaries, but within the striatal boundaries. Then we also have some modes that are kind of associated with this lateralization. So I think this is nice because today we heard about lateral. So this would kind of drive anti-correlations across the two hemispheres, between the hemispheres, without necessarily having like long-range inhibition or like axonal, like synaptic inhibition, let's say. Yeah, and so one thing that is also striking is that first, this type of mode excitation, it can explain long-range correlations and also anti-correlations, right? And if we look at the tissue, here are two types of staining methods, just to be sure that there's no anatomical boundary in the places where we're seeing functional boundaries. And for example, a boundary here, a node, let's say, now that you know a node in waves, can fall in the antinode of another mode, right? So they're not there physically, they're there, they are emerging from the activation of these modes. Another thing is that they can appear very briefly in time. So when we have high temporal resolution, we really sample this a lot. So we are able to detect, this was mode number 7 that appeared here, but at a temporal resolution already of 1 second, you see it's very hard to distinguish this from noise. This is the power spectrum. Even if you sample up to that frequency, you also get noise, like the red is the post-mortem scan. So with high temporal resolution, we can really differentiate the different peak frequencies, artifacts and physiological. Now, the thing with waves, as I said, they obey to rules and principles that are independent from the constitutive elements. So one of the things in waves is that they obey the wave superposition principle, which already, by the way, we capture the eigenmodes of covariance or the principal components. It should be capturing this, so we can simply do this linear sum of eigenmodes. Which is, we have the spatial patterns. It's a collective, it's defined from the whole group of animals. And then we just multiply by the time series from this specific scan S. And what we see is that when you have, so that's another property of waves, is that when you have, like, you can have two standing waves, and the way they are like one in front of the other, like in time, so how they are phase aligned, you can either get a traveling wave in one direction, or you can make the traveling wave in the other direction, or you can even make them rotate. Like that, they're really nice properties that you can get from superposing standing waves. So it creates this illusion of a traveling wave. But what is traveling, I mean, is so it's nice here because sometimes we see it more standing, but sometimes we can see traveling. Of course, the surface of the cortex is on the top, so there's much more happening. This is just one slice, but I think it's nice it's a nice way to explain. So we can get the modes, and then, as I said, like the temporal signature is just the spatial mode multiplied by this, so you just get the 1 times t, the time series. And in the different conditions, in sedation condition, we see these clear oscillations where you really see a clear peak in the power spectrum linking to resonance phenomena. But with light anesthesia, and especially deep anesthesia, this really vanishes. With light anesthesia, we still see some waves, but they're less periodic, and some oscillations. And then with deep anesthesia, they are really, really low, almost like post-mortem. So this points to oscillatory behavior. And so I wanted here to give also an idea for, there are different types of oscillatory behavior or oscillatory damping. You can have a system without any damping, which is a limit cycle, so it just oscillates forever, right? And then, so this is how it looks in the phase plane. It's the gray line here. But then when it's under-damped, which means that it's still, it returns to equilibrium, so the fixed point is at 0. So I don't have here the, well, I can, so this equation here, yeah, this is, does it work? Let me see. So if you have, when oscillate over time is equal to, so it's z time, then you have the natural frequency of the system minus the z is complex, okay, z plus a, okay, and a is a damping coefficient. So how this, it's like, it's the vicinity to the limit cycle, let's say. So the system, if, okay, so how is, if, so there's always a fixed point at 0, okay? If A is negative, if you excite the system, imagine this is real Z and imaginary Z. If you excite, it decays back to equilibrium with an oscillation, okay? But then imagine this is another axis that is A, okay? So imagine this is A equals 0. So if A is positive, and you have another here, if A is, you excite, so it has a fixed point also at 0, but then it has another fixed point, which is the limit cycle. So it can stay like this. But then if you're too far away and A is very, so A is smaller than 0, but then if you have A much smaller than 0, what happens is that you have you excite, but then it just decays back to equilibrium. This gives an exponential decay. So just to illustrate a bit the dynamics, which is beautiful. So, and then you just put that equation decided in MATLAB. I mean, it's very, but the nice thing is you perturb an underdamped oscillator with white noise, right? White noise has all the frequencies, and you get a peak frequency. Of course, you set the peak frequency at a given frequency. You see here the A is close to 0, so it's in the vicinity of the limit cycle. So you add noise and you approximate, so there's this ghost, let's say, or metastable thing, and then it decays. But then if it's overdamped, the system, it will decay with, so you see the power is more like a 1/f. This is important because it seems what we're seeing with anesthesia. So we did this, like we use a measure called the resonance Q factor, which is a bit the peak frequency divided by the full width at half maximum. So it's proportional to the number of sustained cycles before the system decays to equilibrium. And we find that under medetomidine only, so the light sedation, not only we have more modes, but the resonance Q factor is higher. With a bit of isoflurane, we have less modes and they are more damped. So here is the autocorrelation. So here we see several cycles. It decays back to equilibrium with an oscillation. With a bit of isoflurane, it falls faster. And then with med-iso, it's almost the same as postmortem. And this is the 1/E threshold where above it only you consider if you pass that. Well, and they're over them. So we thought, so if this is a completely different rule, is it okay to kind of simulate then brain activity, or can we get a model of what we're seeing in the resting state by just knowing that these are the modes, or assuming or hypothesizing these are the modes of intrinsic modes of the system? Can we just perturb them with this equation of an underdamped oscillation, fitting a bit the damping coefficient to the real-time signals, time series, and the natural frequency? So here, for example, the striatum mode is a bit slower, right? This one had longer resonance, right? And if we just make these things oscillate with these frequencies and then sum everything together, we can also generate a very complex dynamics just with the sum of 10 waves. And when we then compute the correlation matrix and the seed correlation, we see patterns of functional connectivity, but they can be modeled without necessarily having into account the network of connections, right? These long range correlations. So this is a bit speculative, but the thing is, could this damping that we're seeing that occurs with anesthesia, could these anesthetics, how could they act on increasing the damping? And if the damping is a property of the system, could anesthetics actually change the resistivity of the medium through which the waves propagate, the stiffness? I don't know. It's a bit hypothetical, but this is the most we get. Also at higher, with more slices covering the entire brain. So this is seen from above. And the idea is that instead of having like just local units that have their own natural frequency at 0.1 hertz and coupling them together, could these frequencies emerge at the macro scale? They are systemic eigen frequencies, right? And then the collective signal is more like an oscillation of these different modes. So it's just a different perspective of looking into the brain, but still what orchestrates these waves is still completely unclear. But what I wanted here to I don't know, challenge is that these results support this hypothesis that these modes represent the excitation of eigenmodes, which are associated with the universal principle of resonance. And it's crucial to discover what is the physical nature of these modes of the, I mean, you can get it even, this is a kind of pressure wave, but you can get different things, I don't know, and how these waves relate with neural activity, like we heard this morning and many studies, is very important to understand. So this was a collaboration I did with the biomechanics department. So I'm a biomedical engineer, so I'm at an engineering university. And we decided to put the MNI brain like inside the software from engineering called Abacus that they use to calculate the modes of vibration in bridges and in buildings, you know. But so we had 4 compartments. We used the segmented brain from MNI, where we have gray matter, white matter, cerebrospinal fluid, and the skull. And we changed properties such as stiffness and viscoelasticity. We tried to get them from values that are reasonable from the literature, but of course this would need better understanding. And of course, not all the parts of the brain have the same stiffness. So it would be nice to even have more physiological realism. But the key thing here is that if you define the modes by geometry alone, how do you explain that when you fall asleep or when you're in a different condition, the shape of the modes is different or their frequency, right? So there could be something else, so beyond geometry alone, but also considering really the 3-dimensional structure and the properties of the system to define these modes. So this is, for example, changing the viscoelasticity of the cerebrospinal fluid already can change the modes of vibration. So it's showing that these properties can change. And I don't know how I am with time. Yeah, I think this is just the last slide. So before, I've been working a lot with these brain network models. This was even a model where you used these damped oscillators and their damped oscillators at each node, right? So again, it's the natural dynamics, then the coupling term. But then we had this background activity, like we heard Axel yesterday describing that, like this noise that we add to trigger spontaneous activity, right? But what if that noise isn't random, and what if it's obeyed or triggered by this wave dynamics somehow? So can we try to replace this? So can we use the network model? So that would be imagine you generate locally, for example, gamma hertz oscillations driven by neuronal networks, excitation inhibition. But then you also have this wave dynamics, these slow waves, and while the neuronal activity may excite an eigenmode at the macro scale, this can then drive like large amplitude fluctuations in a distant brain area that can also excite the neuronal activity. So there could be some wave neural circular causality. I think today we've heard and yesterday already different approaches suggesting that there's something else. This is slightly different from emphatic coupling or from what Shelley said, but the idea is that there could be something else interacting with the neuronal network at the slower and macroscopic scale that could also be kind of orchestrating the firing of neurons. So the idea is then to show and to compare, so this is new results doing ultra-fast imaging in humans, to see if this type of model outperforms the neural-only or fluid or wave-only models. And yeah, and I'd like to end with 2 quotes. I like quotes, but I think that sometimes we think that we need to find new techniques, new things, but sometimes we could have the techniques already. We have things in front of us, but we just need new eyes. Or yeah, our method of questioning also shapes how we understand the world. And thank you.